So now in this video we're going to look at a bunch of different capacitor topics. First, let's look at the basic component here. So they can have a fairly wide range of appearances right there. These are not surface mounts where they attach directly to a circuit board. These are through holes. That's all I have is through holes. And you put the pins through the hole right there, and you can solder the other side or whatever. This is a solderless board though. You went with this board. But in any case, these are common. The ones that I mostly use for lower value tend to look like this, and I think that's Mylar, and I got these from a kit that I don't really pull too many parts out of. But in any case, the can is a bit different here. So if it's in a can, it's probably polarized there, and if it's not, it's probably not polarized. So that may not always be the case, but that tends to be common. And so the polarized ones, they can store more charge for a given size. So these are about the same size, I would guess, and this one can hold a lot more charge. So that's the main advantage of them. They are polarized though, you gotta charge them in the right direction, whereas the non-polarized ones, you can charge them in either direction, doesn't matter. So now it doesn't look like I have a diagram I put together of parallel capacitors, so we're just going to connect a couple in parallel and look at it. So first off, I'm making sure that they are discharged. We can just go to any point where two parts of the board come into direct contact with each other, and you don't want to do this with extremely large capacitors or ones to extremely high voltages right there. But you can see we got the negative rail, the jumper going there, negative coming across. There you can see a direct connection right there. So that is how we can discharge them. Again, not if they are charged to a high voltage or they have a very large value. Then you'd want to put a resistor between the two to limit current. Now, we're going to wire them in parallel. The benefit of that is that their capacitance adds up. So it's pretty simple, and I could probably just tell you that, and you would understand that, and I wouldn't even have to measure it. But this video, we're going to measure it. So first we'll measure the lower one, and I'm not 100% sure what their values are, and it's auto ranging, so it'll take a little while. But there we go. So it's probably 10 microfarad. It's saying like 11.23 microfarad. They are not, they can be like 10-20% off. That's to be expected, even when they're brand new and everything, and in like decent quality. If you need higher precision, you can get higher precision. So in any case, I think this was 47 microfarad, and it says basically 55 right there. So 55, if we add 11 to that, will be at about 66 approximately right there. So we just put them together, and so if we needed a 66 microfarad capacitor, then I could just add these two together right there, or we could add more in series and whatnot. Again, this is auto ranging meter. I'm not making a good connection. That's the main problem, and this is doing really bad. Am I on the wrong rows? That's a big problem. Okay, there we go. We got the 66 microfarad right there. So if I was getting values that I wasn't expecting long enough, I would double check that I had the connections. I thought maybe I missed a row or something right there, but we did land on the same row. This one's on a different row right there. Alright, so now we got this capacitor back. As I said before, it's not polarized, whereas these other ones are. That's the 10 microfarad there. Maybe I measured this one in the last scene, but they should both be 10 microfarad. But in any case, since it's not polarized, even though it looks like it's a bit larger than that one, we are pretty sure that it's going to have less capacitance. So there it is. This is an auto ranging meter. I just have to set it to capacitor. And one reason why I bought this meter, I don't remember the exact amount of capacitance you can measure, but it can measure higher than the other meters could back when I bought it. I don't have to move the red probe for this one. Other meters you might. So I don't know if most meters now can measure as much capacitance as this one, but back when I bought it, they couldn't. I thought I would enjoy measuring capacitors more than I actually do, but I still like the meter anyways. But that was a big selling point for me, was how much capacitance it could measure. So in any case, there you can see that's about 100 nanofarad. So it takes 1,000 nanofarads to equal a microfarad. Nanofarads are 1/1000th the size right there, and so this is like 0.1 nanofarad, 0.1 microfarad. I mean, 100 nanofarad, and there we go. There you can see that's we're going to just round it to 10 microfarad right there. So this can store about 100 times the charge of that one if you charge them to the same voltage. And make sure you turn the meter off when you're done. So now, as I said before, I don't take mini capacitor measurements. That's because they actually have the value written on them. And then when they come in packaging, usually the value is on the packaging. But the number we're interested in right there is the 104. So actually that's 1 0 and then 4 more zeros for 100,000. I can't remember what J means. I think I used to know. But in any case, we can also charge this up to 100 volts in either direction. But in any case, 1 0 and then 4 more zeros is 100,000, so its value is 100,000 picofarads. But to convert that, that's the same as 100 nanofarad. Now the can usually has its value, if it's in microfarads, written in microfarads. It could be even thousands of microfarads instead of millifarads. But in any case, we got 47 microfarad. As I said before, we measured it though, it was like 55. But as I said before, they can be like 20% off. That's to be expected. And so that side is the side that needs to be more negative, and we can charge it up to a maximum of 50 volts. So we can work anywhere between 0 and 50 volts as long as we charge it in the correct direction. More positive, more negative. And I did write that down in the sheet here to make sure I covered it. So in any case, capacitance is in units called farads right there, but 1 farad, about a farad or more, are supercapacitors. Generally, they're below the millifarad. So that's 1/1000th of a farad. But usually they don't say millifarad. They go into tens of thousands of microfarad. So 1 millifarad is 1,000 microfarad, and then 1,000 nanofarads a microfarad. 1,000 picofarads is a nanofarad. So that's 1/1000th of a farad, 1 millionth, 1 billionth, and 1 trillionth. It gets that small compared to a farad. A farad is a large value for most circuits. So now when it comes to series capacitance, you do that primarily when they're not rated for enough voltage. So when you put them in series, then they split up the voltage, and thus 2 of them in series, you can work with twice the voltage of one of them. Now when current comes into them, it's charging both of them. The same amount of current is going into both of them instead of just going through one. So their voltage actually rises twice as fast for a given amount of current. And ultimately what that means is that it has about half of the capacitance. So it's not terribly easy to explain why it works out that way. Just trust me that it does. But we can also measure it. So again, we're just putting them end to end. And of course we would have other circuitry in a practical circuit. But we're just going to measure their values. So now I already got the meter set to measure capacitance. We already looked at that. Another thing though, this is auto ranging. If you have one where you have to set it to a range of values, then you would set it to slightly higher than you are expecting to measure to get the most accurate. So there you can see a little bit more than 10. They're both 10 microfarad capacitors, but they could have like 20% off usually. That's the value I usually see for tolerance for capacitors. I'm not getting a good connection. But there you can see, they're both basically like 12, little less than 12. So we'll probably have like 5.5 when you look at them in series right here. And there you can see pretty close to 5.5. So the capacitance goes down, they charge quicker, the voltage goes up quicker when you got current going into them, like a lower value capacitor. But the thing is, they're splitting up the voltage so they can deal with more voltage. That's the main benefit. And we're done taking capacitance measurements, so I'm going to turn that off. So now I got the power supply connected to the board, voltage set to 5 volts, but the output is off right now. And so when I press that, not much current moved. We didn't even set off the constant current there. They fully charged instantly. But again, we're only dealing with about 5 microfarad as we saw before. Now I'm going to set this to measure voltage right there. Measuring voltage again. Voltage is auto ranging as well right there. I just have one setting. So we got 5 at the supply. It'll probably be just shy of that. And there you can see just a little bit shy of 5 right there. The thing is though, we have about 2.5 approximately across that one. It's a little bit lower right there. So right when we get to about 2, that means this one will have about 3 volts across it. There you can see it's 3 volts, but now it's going down. So that's the thing I forgot to mention earlier. These are not necessarily balanced. In fact, there's a good chance that they won't be balanced. So it's good to add circuitry to balance that. We will get to that later. So now, the problem was, we had the multimeter attached across one of the resistor. It was similar to this situation, only instead of 100,000 ohms of resistance, the multimeter provides like 10 million ohms of resistance when it is measuring voltage. So this capacitor was discharging, but the power supply still wanted to hold 5 volts across the two capacitors. So as this one discharged, that one charged up. And we saw it went up to like 3 volts until I started measuring this one. And then it started going lower. That was through the multimeter. So one way, if we don't need to worry about these draining terribly quickly, maybe we're holding voltage across them all the time, or we're rapidly changing the voltage, so the current trickling through here doesn't really matter. You can just take a couple, in this case 100,000 ohm resistors, could use higher value too if these are letting too much current go through, but as long as they are equal value, that will work as a voltage divider right there. So it will help keep the voltage of the supply split in half across the two of them. And so especially if you're working like close to that 100 volt maximum, since I believe these are only they might only be 35, no, they are 50 volts. Okay, you know, since they're only rated for 50 volts, if one of them has almost all the voltage for some reason, that'll be almost like twice the voltage that can be across it. So that's okay when they're in series, but not a lone one. So you want to help make sure you balance it in certain situations. Usually when it comes to series, probably best to make sure it's balanced at all times completely, anytime you're going to do that. So now you can see we got 100,000 ohm to the positive supply coming to where everything connects together, and then another 100,000 ohm resistor going to the negative supply where everything connects together. That capacitor to the negative supply. We will zoom back, and again, it's auto ranging meter, just have to set it to voltage, it does the rest. We're going to have about 5 volts across here, and I got the probes backwards. You got a negative voltage there, no big deal, just because the probes are backwards. So I realized that when I saw the negative voltage. That's what that means. So in any case, there you can see 5, and we come here, and we got 2.5. So now we're going to look at a couple things. So I'm going to pluck that, and now you can see it really rapidly goes down because it's going down a lot faster because that resistor has a lot less value than resistance, I should say, than the multimeter. So we go down, and now we're going to zoom back and look at something else. So you can see this one is discharged. That's why I'm looking at that one. The other one has the full voltage right there. So what we're going to do is we're going to turn off the power supply, and then the capacitors will discharge to a total of 0 volts. But we're already pretty much 0 volts right here. And this does provide actually, I believe, 0.6 volts negative. So it's going to be a little bit worse than what it would be if it actually just dropped down to 0. But there you can see, we had a negative voltage there. And again, now it's discharging. But you can see we actually went negative on it. So not by a ton, you know, but it did go negative. That is the main thing right there. I'll turn the power back on. So it was positive because it charged up when we turned the power on. So if these two are just in series, a lot of circuits, the one that's charged will negative charge the other one, as you can see there. And if it doesn't have, current doesn't have anywhere to go or anything, no balancing, the resistor helped with that, then, you know, it could be dangerously reverse charge for a long time. That is a possibility. So again, be careful when you put them in series. Alright, so now we're going to move to this circuit here, and this is demonstrating a couple of things. First off, that the capacitor can store charge. So we're using a, you know, pretty high value here, 1000 microfarad for most circuits. So there's a lot larger values, of course, and then there's supercapacitors. But most circuits, you probably won't be using more than 1000 microfarad. So it is charged. It's been charged a while. Actually, no, the power wasn't on. So now it's charged, and when I move this jumper, now the capacitor is just sitting there with its stored charge. And I'm going to come to that side of the resistor, and when I make a connection, you can see the LED gets bright, you know, pretty bright for about a second, and then every second after that it got less bright, and after about 5 seconds approximately, the LED turned off. And so the capacitor is going to charge as quickly as the power supply will give it current right there, because there's no resistor. I got current limited on the power supply. And once it's fully charged, again, we can complete the process. So it's working kind of like a little rechargeable battery. But, you know, if you had a coin battery, which would only be like 3-4 volts, then it could power that LED for a real long time. Coin battery would be even smaller than this. At that lower voltage, though, it could power this for hours. And so it doesn't hold much charge if you think of it in those terms, capacitor versus battery. So now the reason why I mentioned 1 second is because that is the RC time constant of those two components right there. You take the resistance and multiply it by the capacitance, or vice versa. It doesn't matter when it comes to multiplication which one you do first. So 1000 microfarad capacitor is the same as 0.001 farad, or millifarad. And so in any case, that's how many farads it is. You do the multiplication in farads. So you take that number, which is 1/1000th of a farad, times 1000 there. So 1/1000th times 1000 is 1. That gives you 1 second for the time constant. So that's not how fast it discharges completely. It's about 2/3 of that time. Charge, I mean, is goes down. And then the next second, 2/3 of what's left goes down. And then the next second, 2/3 of what's left goes down. And so on. After 5 time constants, you consider it fully discharged. So now we're going to look at the RC time constant in action. You can see that we have a resistor and the capacitor in parallel, and once I apply power, the capacitor will charge. We also have the oscilloscope there, the alligator clips coming in these jumpers, measuring across these 2 points, and that was just stray voltages from my fingers or something like that. But in any case, power supply is off. It's 7 volts, so it's current limited at 20 milliamps of current. But when I turn it on, the capacitor pretty much instantly charges. Again, it didn't have you know, more than 20 milliamps current, so it had a little bit of a slope. But in any case, there you can see, charged basically instantly. So it's being charged through this jumper. Once I remove this jumper, little current's also going through that resistor. Then the voltage of the capacitor is going to go down because it's going to be discharging through that resistor, and we'll see the RC time constant curve. So there you can see it dropped really rapidly, and then it slowed down over time, and at some point we just consider it completely discharged. So I actually like where that landed right there. So right about that point, we cut it down, and there you can see, as we said before, there's an RC time constant of about 1 second. So we got 7 volts. Voltage doesn't matter. You're going to move in that RC time constant, so that's based on the capacitor value and the resistor value. You multiply them. We had 1 second, but there's 5 time constants before it's considered completely discharged. So right there, that's about where you consider it completely discharged. So not very charged before that, and then it's going to go trickle down a little bit over time, but that's practically 0 right there. Now we're going to look at the opposite. Well, the capacitor is charging, it will give us the same. So that's to the negative supply there. We're in parallel with the capacitor, with that jumper. The resistor wants to charge the capacitor, but it's going through that jumper. It will charge the capacitor when I remove the jumper, and there you can see voltage is rising right there, and should be giving us the exact same timing that it gave us before, but now just in the opposite direction. So I think I paused it in a pretty good spot again right there. And so again, 1 second is about 2/3 of the voltage change right there, and then the next second is about 2/3 what's left, again and again. So let's go 1, 2, 3, 4, 5, and there you can see that's when it's about, you know, the flattest. And now we're going to move to a circuit that's similar, but a bit different. So we saw the curve that was due to the voltage change across the resistor as the capacitor voltage change. Now we're going to set current. So we don't need the resistor here. The resistor will set a maximum current. Otherwise, the photodiode here, which is reversed by a short lead cathode more positive, long lead anode headed towards the more negative. But in any case, the photodiode is going to set the current based on how much light falls on it, and it's not much current. So it's going to easily flow through the resistor, it's going to limit current, and the capacitor is going to charge. when you charge a capacitor with a steady current, its voltage rises steady. They are linear. So now in the last scene, I forgot that little jumper right there that connects to the two sides of the switch when you close it so that the capacitor can discharge, get down to 0 volts. So we are working with 7 volts, and this is going to go down in brightness at some point because we're operating on battery. But we got about 7 volts there. This doesn't line up perfectly, but we got 7 volts charging the capacitor until I press the button right there. Then it dropped down instantly. We had an instant discharge, and my lamp is at its looks like the brightest setting based on how quickly the voltage is rising. So it's rising steadily right there. We can slow down how fast it rises right there by lowering the lamp, but ultimately it is steady. I think something might not be connected perfectly there. That's why it's kind of wavering. You know, slight movement for me moving or something might have bounced it. But there you can see it's rising steady. So 1000 microfarad capacitor in this circuit is a bit high, as you can see there. It's taken quite a long time for that to go up, and I had a 47 microfarad capacitor, but there it is. So we will swap the two, and there we go. So you know, pretty much fully charged there. We'll press the button. We can zoom in, see it better, and release it. There you can see. So it was a ramp. It rose steadily. That was at the brightest setting there, and there you can see it's slower because of less light. But you make a brighter light and it will change. Ultimately, you can look at accumulated light levels, like with the larger capacitor. You saw that it rose slowly, but if you get it brighter, then it goes faster, and then if you get it darker again, it'll go slower. So the higher it goes, that means you know that it had more light on it over a you know, given period of time. If it stayed like really low, you know it was dark most of the time. Whereas if it was like really high, you know that it was brighter most of the time. And now we come back to the diagram. So I had 7 volts at the power supply instead of 5. Doesn't matter. That's kind of a lot of voltage for that resistor. But again, it was the light photodiode, I mean, that was setting the current, not the resistor. So it was taking the voltage off the resistor. Shouldn't overheat. And as we saw before, yeah, more light, it charged faster and everything. But when we had the larger value capacitor, it took longer. So a lower value capacitor will mean that the voltage rises quicker for a given light. So now a lot of times you'll have a capacitor, I think you call them smoothing capacitors under most cases, but their goal is not really for timing or anything. They just try to maintain a voltage for the most part. It's pretty easy to change the voltage, but not extremely rapidly. So when it comes to the light dependent resistor right here, so it's a resistor. The resistance changes based on how much light falls on it. It doesn't set a current, it just has resistance, and then the voltage that is across it will set the current, like a regular resistor, other than it changes when light falls on it. So normally, you know, it still makes an okay voltage divider, no problem. But I have a flashlight and a lot of LED lights. They do not turn on steadily. So when they dim, even the brightest setting of the one that I have, it's not on steadily. It's turning on and off rapidly. And then it has a lower setting. It's off longer than when it is brighter. That's how it adjusts the brightness. So your eyes, you see like a steady light because it's quick enough. But sensitive circuit, like our oscilloscope will see, you see the voltage bouncing around as I shine the flashlight on the light dependent resistor. So we can add a capacitor right there. So that's where we're going to measure. And again, with steady light, doesn't matter if you have the capacitor or not. You'll get a steady voltage based on how much light is falling on the light dependent resistor with this voltage divider there. So it goes up when it's brighter because the LDR here conducts better. And then when it gets dark, it starts getting to where it's like doesn't even exist anymore. Current doesn't flow through it anymore. And you'll have 0 volts going to ground if it is dark enough. So here you can see the voltage we got when the lamp is at the lowest setting. So as I said before, that resistor helps pull the voltage down when it is darker. But we get it brighter, the light dependent resistor pulls the voltage up. I removed the capacitor though. This light appears to be on steady. So now I'll grab my flashlight right here, and I'll zoom it in. And there you can see we got bouncing all over the place right there. It is not steady. This has a side light where you do get a steady voltage right there. So you could see, you can monitor like that voltage level. But really, you know, you got an idea where that is. But if you have like a sensor or something trying to respond to a specific range of voltage, usually there's a little hysteresis too, but usually hysteresis is less than that. So you can go as large as value you want on here. If you go really large, it might take a little bit of time to change. But in any case, I did some testing. It looked like 47 microfarad did pretty well. There you can see we can still change it pretty quickly, but when I get that particular light right there, now it's pretty steady. So that is it's the brightest setting, and I should have did the medium setting before. There you can see it went down a bit. So again, it's probably not as straight as if we used a larger value. We can do that. Let's try the 1000 microfarad. So whenever you learn something, actually test it out like this. You know, read about it. Primarily, I want you to read this stuff. This is just, you know, practical demonstrations that I'm showing in these videos. Ultimately, you want to read everything. So the display just goes dim because I got it on battery there. And so now, yeah, I'll go bright. There you can see it still changed pretty quick right there. Not as quick as the other one. And we'll dim it down. And there you can see. So we're back pretty far. Sorry about that. We got a smoother line than we did before. We got the other settings there. So that's brightest, and it's smoother than it was. So if we needed it smoother than we had it before, you just go with the higher value capacitor. It is that simple. So in any case, a lot of capacitors, they're just making the voltage more steady at a particular point. This power supply, if you bump it, the capacitor is probably helping there too. There you can see we got dips in voltage there. So that capacitor was steadying it. The best spot for that problem is just to put it on the rail right there. And then when we get a, you know, drop of voltage, just a little spike, you know, that capacitor can power the rails until that recovers right there. And a big enough capacitor, you won't notice any voltage change, just like with this circuitry there. So a lot of times you'll see a capacitor doesn't look like it's doing anything, but its goal is to help steady the voltage at that point. So in any case, long video. I meant to do a long one this time, and I meant to cover a lot more over this period of time, but it took this long. So I'm just going to end here. I thought I was going to use more diagrams than I just drew for this one. So I hope you enjoy. Make sure you check all the links down below. Click like, subscribe, and all that. All the links below help a lot, so please check them out. See you in the next one.